We are the Burns McDonnell Jackrabbit Substation, a team of four electrical engineering students, faculty advised by Dr. Timothy Hansen.
Hi, my name is David Skora, and I will be going over our lightning protection design. So the purpose of the design was to protect all equipment against any lightning strokes that would be in the area. We had some specifications we had to follow. First, we had to follow the IEEE standard for lightning protection. We were required to use the fixed angle design method, as our sponsors were most familiar with this method. The failure rate must be 0.1% or less, and the maximum mast height was to be 66 feet and 2 inches. So our design of the lightning protection was based on the final layout of our substation. We originally had 6 masts already in the substation, and so we just needed to keep adding masts until all the equipment was enclosed. So the protection that each mast provides depends on the height of the equipment it's protecting and whether it has an overlapping versus non-overlapping radii of protection. And IEEE determined that non-overlapping radii offered more protection, as lightning was more likely to hit that higher object than it was to hit the equipment below it. And so you can see our final protection there on the right. As far as results go, no protection can be 100% effective, and so we calculated the failure rate. That's what's being done on the right. And our value falls within the specified failure rate of 0.1% at 0.003%.
Hi everyone, my name is Jacob Wall and I'll be discussing the grounding grid today. The purpose of a grounding grid is to ensure safety in the substation during fault conditions. We designed ours to follow IEEE standard 80-2013. For specifications, we want to limit touch and step potential. Touch potential is going to be the difference in potential between equipment and the person's feet when they're touching the equipment, while step potential will be the difference in potential between a person's feet when they're walking through the substation. Using our soil resistivity chart, we found out that a maximum grid size would be 30 feet. We chose a more conservative 25-foot grid to maximize safety. Here's a preliminary design of our grounding grid. The grid expands past the edge of the fence to get fault currents away from the substation as quickly as possible. The purple dots are grounding rods, which are 20-foot long rods pounded into the ground. These help to get fault currents deep into the soil where it's less resistive. So the grounding grid was simulated in a software called CDEGS. We were not able to do the simulation ourselves. Our sponsor had to do it, as a key of CDEGS cost $20,000. But for our step potential, the maximum allowable step potential, or the maximum safe step potential, would be 2,220 volts. In our substation, the maximum simulated is only 407.8 volts, so we are way below the limits in that area. For touch potential, the maximum allowable is 672 volts, and the maximum simulated is 481.27 volts. The best part about this is around our equipment in the middle of the substation, we're getting less than 81.1 volts of step potential.
Hi, my name is Noah Anderson, and I'll be going over the DC battery study. Our purpose is to design a lead-acid DC battery bank to provide power to all the substation loads. We must provide power for 8 hours in a worst-case tripping scenario and be able to recharge those batteries within 8 to 24 hours. Our worst-case tripping scenario would be a fault on the transformer causing breakers 1, 2, and 4 to trip. Our load classification can be seen on the right, including our first minute, continuous, and momentary loads. The total amp hours of our loads were calculated using 3 battery correction factors of temperature, age, and design margin, which were 15, 25, and 10% respectively, giving us a total of 178.126 amp hours. Our battery charger sizing duty cycle was split into 3 different blocks of first minute, continuous, and momentary. We were able to use these calculations to find our amperage rating of 13.16 amps, which we increased to the 16 amp standard battery charger size. This gave us 17.8 hours of charging time. So we ended up deciding on 20 power safe batteries, which gave us 153 amps of single minute capacity, as well as 17.7 amps of continuous capacity. These batteries are expected to live for 20 years.
Hello, my name is Tyler Jorgensen, and I'll be discussing the AC system sizing study for the Jackrabbit substation. The purpose of this study was to properly size station service voltage transformers, SSVTs, which are line to ground, single-phase transformers that step down high voltages to the usable level to supply AC loads. The specification was that each SSVT set had the ability to supply more than 100% of the worst case expected loading while maintaining redundant protection. Demand factors, which are a measure of how often the load will be expected to run, were considered for the seasons of winter and summer. Loads such as transformer fans have a demand factor of 1 in the summer to maintain operating temperature, but are reduced to a factor of 0 in the winter when sub-zero days are common. The top 5 loads that affected the total demand include breaker heaters, roof vent fans, HVAC, yard floodlights, and the 125-volt DC battery charger that was selected in conjunction with the DC battery study to charge at the recommended rate. Under the worst case loading conditions, summer would be the limiting factor at 29 kVA. Therefore, each recommended SSVT is rated for 35 kVA, which accounts for 83% of maximum capacity. In conclusion, the lightning protection was designed to IEEE standards and exceeded the goal of allowable strokes. The grounding study at both touch and step potentials below the maximum allowable voltage. The DC batteries are able to operate for the minimum 8 hours, and all AC substation loads can be serviced at any time of the year.